Well, hello everybody. This is Sylvain Rochon, the Peaceful Revolutionary. Welcome to everyone. This is another Revolution Science bit. I was going to do something about more humanistic, more about the terrorists and the conflict between Russia and all this stuff that's brewing over in Europe. But I feel there's a lot of people that are doing that kind of thing, even though it's really close to my heart. Something just came up on my desk like today while I was preparing to do something that was, something that happened in Peterborough, which is between Ottawa and Toronto, that really showed a lot of hope for the world. So I did want to do something about that in relation with, a terrorist attack in Syria and these things. It's really great what people can do. But I will keep that for perhaps next week or the week after that. I'm really excited about this one because I really love about things that are really big, like really world-changing, revolutionary. Because we're all revolutionaries, right? We're peaceful ones. We want to know what's going on. We want to change the world. We want to do really great things. And the bigger we dream, the better. So in this case, it's another physicist paper, another physics paper that I wasn't aware of. And this one was published in Physics Letters B, which is an online journal. It's more theoretical, and it was a work that was in conjunction with an Egyptian man, and in Giza, Egypt, was a professor there, and another professor of physics that is in Alberta, Canada, which is I live in Canada, and they collaborated in trying to define the universe in a different way. And this is really interesting because about 2 weeks ago I did a paper by Nassim Haramein, who was defining how atoms and how different things kind of rotated and where it's actually similar and everything was kind of universal. So it kind of rung with me to actually run with this, because what they're saying is they kind of decided to approach the Big Bang Theory or not the Big Bang Theory, but the beginning of the universe using a different set of mathematics to approximate or to base on their stuff on, and to see whether or not using this different mathematical model would end up giving a different explanation of where the universe comes from, how old it is, and that kind of thing, and whether or not they could come up with a model that would work with current observations, which is really important, because with the Big Bang Theory, with these theories of the universe, these are astronomical timelines and distances. We can't really test anything. Things in the universe are moving extremely slowly from our perspective, from our relative perspective. So we can't really wait 100 million years to see, if something actually goes on the way we think it is. So we're using mathematical models, and we're using small time span observations, and we use the math to see whether or not it fits with the actual universe that we observe around us. Now, the Big Bang has served us really well in kind of approximating a lot of things, and because the reason that it was around for so long as a theory is because, in fact, you use the math and you can actually model a lot of the observable universe the way we see it, which is awesome. But it has a few problems. It's not perfect. The first thing that is problematic is that it automatically, it means, because it's based on geodesic mathematics, which I'm not familiar with intimately. What it does mean, though, is that it guarantees a singularity or singularities. And because we're talking about the beginning of the universe, it obviously guarantees, because it's geodesics mean that the things converge at a certain point. The math always converges. So if you're talking about the beginning of the universe, it means that it's going to converge. Everything eventually converges in a single point at the very, 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 very beginning. But that's because of the choice of math that the mathematicians took. It doesn't necessarily mean that that's exactly it, because we can't observe the original of the universe. What validated the Big Bang Theory was basically that we use the math with things that are observable, it fit, so there's the assumption that, well, that's the way things are until we figure out better. And that also means, like, for now, we assume that the universe was 13.6 billion years old, and it started up with all the matter, came to be in the small pinpricked, and then exploded, and eventually it's going to contract back by forces of gravity and things back to its original point. It doesn't explain anything because of a singularity of the whole universe. What happened at the moment of that all the matter is there, and before that, like how can this all the matter be in this one point and everything else be completely empty? It doesn't make a lot of logical sense, but the math works out that way, so we kind of ran with it because it worked, right? The second thing that's a problem with the Big Bang Theory is that if you look at the force and you do the math, you have to assume that there's going to be a lot of dark matter, which actually creates a lot of gravity that is missing in the mathematics between in the universe, and also dark energy. It's a lack of energy. So these are things that we can't see. That's why we call them dark. We can't see, we can't touch them. We don't really know they're there, like as far as tangible touch them. But if the math has to work, they have to be there. They have to exist, and we have to include them in the mathematics to balance things out. So these are things that are a problem. So there's a lot of scientists that are they want to, because we want to define, we want to be to prove that this is how the universe is and how it began. So a lot of scientists are trying to find dark matter, find dark energy, to know how to measure it and things like that, so that we can say, haha, here it is, here's the gravity. Now, not only does the math work, but we can also identify, touch, measure, the dark parts. So it's always interesting in looking at other theories with other mathematical models that can work with the current universe and dictate something different, that assumes something different. And this is the case for this paper, which is called Cosmology from Quantum Potential by Ahmed Farag Ali. This is the guy from Egypt, and Surya Das. He's the one in Alberta, Lethbridge, Alberta. And both are professors. The credentials are they're teaching at legitimate organizations and universities. So even though it's not a peer-reviewed paper, from what I can tell, it's a great theory to kind of spin off, and it also has its problems. It does. Okay, it's not hey, let's shove back the Big Bang Theory and let's use this one. The science is not solid enough. It's going to take time and other research, just with something new, to see if it's better. We have to be a little bit patient, keep looking, and keep researching, using the new paradigms, being radical and revolutionary. We have to look at different ways to see things to improve our case, right? So the issues with that is that it starts off, instead of using geodesics as the basis, which, and the choice of these geodesics was actually quite logical. The most particles in the universe follow a geodesic pattern, so it's fairly logical to use that. And also, it's well, having singularities, especially a starting point with the Big Bang Theory, is very logical from a philosophical point of view, because back in the day, like right now, it's less so, but many years ago, a lot more people were very Catholic or God-fearing, and so the idea of a beginning that may have been like a finger snap by some godly being, out in the earth somewhere, it probably made a lot of sense. So, there's that. The new theory that came out to perhaps challenge the Big Bang Theory, the cosmology from quantum potential, is based, instead of basing it on geodesics, it's based on quantum trajectories, which I'm completely unfamiliar with. But from my understanding of how the math is set up, is that in this case, it's a little bit opposite from geodesics. It's quantum, the way quantum objects move. It kind of approximates with these quantum objects moves. And the basis of the math, the way the math works in itself, it guarantees that there will not be singularities. Now, according to the writing, the authors did not do this on purpose. It's just they wanted to use another model to see if it would work. So they're not trying to ignore the singularity principles. Singularities may exist in the universe, and why not? But I mean, they just took a different approach according to them, and some interesting things happened though, because since this math involves no singularities, that means there is no Big Bang, there's no starting point, because the singularities cannot exist under this particular mathematical model. And it means that the universe is infinite in time and space. I mean, there's no mention of size, but you can kind of assume it has to be there, either a certain size or infinite size. I mean, it doesn't move, doesn't change. There's micro movements, but not at the universe level. It's eternal. It has no beginning and no end. It's always been there. It always will be, and things kind of move around it. And second assumption they have to do is that the universe is all bathed in this quantum fluid that is really, really small particles, like a little bit like a really, really small quantum water, if you like, and that has gravity inside. So you're avoiding all the dark energies and the dark matter, but you have to make an assumption of a different sort to make the math work. And right now, I don't really know the difference. In the description, I'm linking a few articles, including the actual scientific articles. So if some of you are deep physicists, you can go and read more about it, comment and whatnot, and kind of describe stuff more fully to people. No problem. But I just want to give a summary from my understanding and kind of give you a perspective from it. So it's really cool. I mean, it means there's perhaps more ways to see the universe that are just as valid. Because in the case of using quantum trajectories, what happens is that you still have failings, but they're not worse than the Big Bang theory. So it raises the question of the fact that we may not even know what the universe is like, because you have two theories that seem to be fairly equally would have equal failings and positives in many ways, and they're very different in describing what the universe is like over time. And my main point in all this, is that when there is a theory, even the theory of gravity and all these theories that we think are rock solid, theory of evolution, I did a blog on that, and I punch a few holes in it where it's kind of messed up a little bit if you look at it. It's like an incomplete puzzle. You can't take it for cash as if it's absolutely true and that's it. We don't need to look at it anymore. Science does not work like that. We are always progressing and figuring out new things, and we're almost always wrong. But we're moving ahead towards what is true, and we're defining it better, and we're getting better at defining things, and we're getting closer to how things are. In particular, with concepts from way, way, way back in the past, or the huge things we can't measure in a microsystem like in a lab very easily. It's really hard. So we're using mathematical models, and we kind of make a lot of assumptions, and we can't really test it fully to see if it's really good. So once in a while, you have other physicists and other scientists that kind of shake things up. It's like, look, instead of making this assumption, let's make that one, see if it works. And if it works just as good, it's like, well, who's really right? We don't really know. But it allows us to ferment these ideas and to move forward with science, with new ideas and new vision of the world. And in some cases, it actually helps with peace and harmony. And these really nice concepts, because a very established theory that still has holes, if it becomes dogma, like the theory of evolution, for example, and the Big Bang theory, which are great examples. There's even wars and like super duper violent conflicts that come out of that. We want to avoid that. Like, let's keep the information flowing. Let's keep making assumptions, but let's not create dogma from scientific theories, right? So anyway, I want to end this blog with this thought. I just wanted to do that. It's really exciting. I hope we keep kind of looking at things in a very nice way. Maybe soon we'll figure out things in a better way with our technology and vision, and new telescopes coming up in the sky. and we'll figure it out. I mean, that's a given time. In the meantime, let's just keep our minds open and look at things in innovative ways, and focus on what's really going on the planet, which is more down to earth and not about looking at what happened 13 billion years ago or beyond. More about the now and the next 5 years perhaps. So anyway, peace out, guys. Hope you enjoyed this, and keep the science coming, keep the good thinking coming, and we'll be catching up to you in a bit. Oh, before I leave, I'm going to have a really, really cool visitor with me for about 2 weeks. Not sure I'm going to be doing blogs for the next 2 weeks or so because I'm going to be traveling around. I'll try to do a short one, especially if there's something really nice out in the public to keep things going. But between now and Christmas, you know how it is. There's maybe a slowdown in blogs, so don't worry. I'll get back to it after the holidays. All right, have a good time. Enjoy. Bye.